Hello and welcome to C++ 101 Week 6, Part 2. Like I said at the end of the last video, we had some small technical difficulties where Comcast decided to disconnect me from the internet and made it impossible to continue the class. So we rescheduled for today, and we're going to be picking up right where we left off and get into dynamic memory allocation and data structures. So again, I'm here, and I'm Nelson, and Gavin's here.
Hooray! And I'm all kinds of ready for C++ action.
Sweet. So let's talk about dynamic memory allocation. So we've discussed quite a bit throughout this series. I've really wanted people to get familiar with the concept of a stack, particularly the stack that data that is required for our functions to execute is required to make my tablet completely freak out and stop working, and which results in me having to plug it in instead of using the wireless dongle that I spent $40 on and wish I hadn't.
You've got to see, now that's, yeah, those dongles aren't the best in the world.
Yeah, there we go. It's plugged in. We should be good. Okay, so let's talk about dynamic memory allocation. So we know that we have the stack. So if we have an int main function, and let's say it has an int number, and it's assigned to 10, and this is the extent of our main function. You know that by writing this C++ code, the resulting thing that happens at runtime is our program's memory is principally represented as a stack. So when the main function gets invoked, the main function gets added to the stack. So the main function in this case has a single integer local variable, which means that the size of the main function on the stack is at least 4 bytes. And the reason I say at least 4 bytes is because there's a little bit more to the stack than just local variables. We still have things like parameters. We still have things like return addresses. But at least 4 bytes is allocated to make this main function work. However, we have a problem here. We have a very, very big problem with our code that's going to prevent us from expressing anything more than the most simple of programs. And that problem is that this 4 bytes is calculated at compile time. The compiler knows that we only have one local variable, so it emits the instructions to allocate that much memory and no more. Meaning, if we were to want the user to be able to type in an undefined amount of numbers, we would have no way to actually grab more memory than what we are made available to us when our program starts. So this is obviously a huge problem and will prevent us from writing almost really any type of useful application. So what we need to do is we need a way to ask the computer, ask the operating system for permission to use more memory during the execution of our program, and we can do so in a way that isn't statically defined. So the fact is, our program memory still has, our stack frame still has to be computed. So does anybody know what feature of the language that we can use in order to access memory that is made available to us dynamically? What feature allows us to do this? What feature will allow us to reach in and mutate and reference data that we don't necessarily have at compile time? And as people said, they're pointers. So let's talk about... You what?
I said hurrah.
Yes. I'm
In
going
an
to
excited fashion.
Rewrite it in a little differently in a second, because I'm going to actually do something interesting. I'm going to write a program that will dynamically allocate an integer. Okay.
Hmm? What?
Was that...
That will dynamically allocate
an integer. Here's what happens when this code runs. First thing that happens is that the main function gets invoked. And because the main function gets invoked, steak. No. See, I just ate before class, so I'm thinking kind of in terms of food. We don't have a steak, we have a stack.
Could have a stack of steak.
Yes, and go away. There you go. So we still have a stack, and within the stack we have the main stack frame. And the main stack frame is going to contain, in this case, an integer pointer, which on a 32-bit operating system will be 4 bytes. However, what happens when we do this? This is the important bit that we're going to be talking about. The new operator is used to allocate additional memory on the heap. The heap is the bit of memory that our program is allowed to allocate additional memory in. And the location of the memory isn't really technically important. The operating system can give us access to anywhere it likes, to be honest. But what happens when the new operator gets invoked? The new operator informs the operating system, and that was a horrible line. Wow, that was even worse. I got this. The new operator will allocate 4 bytes onto the heap. It'll allocate an int, which again is going to be 4 bytes. Then the new operator will return an address into our integer pointer. So this address may be 0x54, so hexadecimal 54. It doesn't matter where that is. Here's the important thing. This 4 bytes lives on the heap. When the main function is ended, and we didn't have this line right here, what we would get is this memory would still be valid, which gives us a nice bit of functionality that we can take advantage of. So for example, remember how earlier we had a product pointer function that returned a product pointer? And we realized that this is bad because if we return a pointer to memory that's allocated on the stack, that memory will be deallocated, and that variable that we assign the pointer to will turn into a dangling pointer. However, if we do this, here's what happens. The new operator allocates a product onto the heap. That's still, I can't spell when I'm writing. When I'm typing, I can.
Oh, I see.
No, to an extent.
In the same way, I can't speak when I'm making a noise.
Anyway, what happens here is what we're returning now is not memory allocated on the stack frame that's allocated when we invoke the create function. What we're returning is a pointer to an address, and let's say this address is 0x64. So we're getting this address back, and then this product pointer will be returned into whatever function invokes it. And here's the great thing. This product on the heap will still exist and be in scope. It'll exist and be in scope until one of two things happens. Our program ends, or we invoke the delete operator. The delete operator must always be matched with a new operator. The delete operator, not surprisingly, will delete any of the memory that's allocated to the pointer that we're deleting from.
Which is just similar to closing any sort of stream that you've opened.
Otherwise, you'd be leaving unmanaged resources elsewhere. So let's go ahead and bring this into some code.
And presumably in that picture, the product returns its address to the stack.
Yes, yeah, that is important. The
You can draw the arrow in.
Well, actually, in this
sure.
case, it is a little bit more complicated because we're simply returning straight, so it doesn't actually go on the stack in the same way a local variable does. But if I were to have instead said,
if you called create from in main, for instance,
right, if I had, if I had said product pointer p equals create. What this looks like now is the main stack is a product pointer, which still exists on the stack. The pointer exists on the stack. However, the heap will contain the data of product. So this variable is still on the stack, but it's only 4 bytes on a 32-bit operating system because all it is a reference to somewhere else in memory.
Makes sense. And also, and obviously, the compiler can work out how much space to make room on the stack for that.
For the pointer.
At compile time, because it knows for the pointer exactly, yes, because it knows at compile time what the return type of create is.
Mm-hmm.
So it knows how much space to allocate.
Yep. But of course, at runtime, we could be allocating a billion things.
Any amount of space.
Right. Within the constraints of your address space, which on 32-bit processors is 2 gigabytes.
What is the limit on x64?
It's just big.
It's cha-ching.
Okay, so people are talking about what a memory leak is. A memory leak is when this is technically a memory leak, although it's not a bad one or a really bad one. You're not going to notice this because the fact is our program exits immediately after instantiating the product. So this, although it is technically a memory leak, it's not a very important one because, yeah.
By that token, presumably, though, it's unlikely that, I would imagine the majority of memory leaks that occur are of this sort of scale. I mean, it's not going to be one monolithic memory leak that you find in your program, is it? Or is it?
Typically not. You generally don't.
It can be like hundreds of little ones.
Yeah, that's what gets you. That's why they're also hard to find, because you could run a program in testing and maybe your application is only running for maybe 6 hours at most for your QA team. But you don't think to test your program running for an extended period of time, and then after 3 days you'll notice that your memory has gone up to 2 gigabytes and your program crashes. So a memory leak is when you do not...
And you get your AAA manufacturer employee of the month certificate that day.
Yep. So basically a memory leak is when you allocate memory and you do not deallocate it. So let's look at code.
Code. Boo, C++. No. No, I love C++. That's why I'm here. Yeah, and I love that you love that I love it. I still want the steak, though. Particularly when you said that the steak was 4 bytes, I thought it's a very small steak.
Who said that?
You said the stack was 4 bytes, and because it was just after you said about the steak, and I thought, oh, that's a very small steak, 4 bytes. Anyway.
Well, 8 nibbles. I love that word.
Nice moist nibbles of steak.
Yes.
So that's some code.
It is some code.
Does it work?
It does work.
Wow.
Okay. Oh, come on.
You know, you said it works.
This is an example of dynamic memory allocation. I want to point out really quickly that what we're doing here is not necessarily the best example of why you would want to do dynamic memory allocation. That being said, I want to make sure that people understand what's going on here. So, are there any questions about the syntax that I'm using? Are there any questions about where memory goes when I run this program? Are there any questions about that sort of thing? Because this is the most basic form of dynamic memory allocation. We're going to be...
So, are there any questions other than why are we doing this?
Because, well, we are going to be doing some really fun dynamic memory allocation stuff soon.
Well, I mean, even so, already, depending on the length of the product name, you are saving an unspecified amount of stack space.
Well, yeah. And also the display method or function, instead of taking in a whole copied product, it simply takes in a pointer to a product, which is faster to invoke than if I were to have not had the pointer symbol there.
And that's the thing. I mean, it is, again, we're coming to subjects that are to get the best, to give the best example of them requires quite a more complex example to go through. It's a bit chicken and egg syndrome.
And the homework tonight that I'm going to be giving out is going to be instrumental for people to understand this. I was so tempted to do what we're doing for homework as a demonstration, but I really want people to work on it themselves. We're going to be writing a vector here in class, an implementation of the vector. Not a templated one, a non-templated one. And then for homework, I'm going to ask people to write an implementation of a linked list.
Ooh.
Product is a pointer to a new product. Yes. This is a pointer to a product that is allocated on the heap. The new operator specifies that we want to allocate memory onto the heap. How much memory? Well, however much memory this product structure requires. Now, if you'll remember, string is a class, and string does its own dynamic memory allocation behind the scenes for us. However, I think the class itself is 32 bytes wide, if I'm not mistaken. I can't remember. It's implementation specific. So that means that when we invoke the new operator, at least 32 bytes gets allocated on the heap. And then what gets returned is the address to where that memory was allocated on the heap. So now we can reference it via the pointer. In the product pointer create function, does that mean that the function is a pointer or returns a pointer? This function returns a pointer to a product. This function is not a function pointer, and function pointers do exist. We will be having some fun with function pointers, not in the 101 class though. But they could be really fun. You can do some awesome stuff with function pointers. I once wrote a reflection system that's similar to .NET's reflection in C++. It was great fun. I spent like a week on it and got it working really well. And then I realized I had just spent a week re-implementing a feature that was available in C#. But it was a really fun project to work on. And it made use of lots of function pointers and templates.
Yeah, I know that feeling. I taught my computer music theory. I was quite pleased with that.
Yeah, I remember. Yeah, that was your first big project?
Yeah, it took me 6 years. And I didn't have a teacher.
How did this get back up here? Go away. Why would you return a pointer? I thought the whole point of pointers is that you don't have to return anything. That's not necessarily true.
Somebody forgot to turn their phone off. You know that's a sacking offence in the music business.
Well, yeah. Give me a sec. There we go. No.
If I was in a room with you, it would at the very least be a slapping offence.
Okay. I thought the whole point of you don't have to return anything. No, the point of pointers is that we can point to bits of memory that are elsewhere. The whole point of a pointer is to reference memory that isn't immediately available as a local variable. A pointer can be used to reference memory that's on another function's stack frame, or it can be used to point to memory allocated on the heap for us. So,
and if you flip back to the whiteboard for of this example, you can see just that here.
Actually, I'm going to fix this example real fast because I started with the int thing and then I realized int was kind of stupid.
Yeah.
So,
but it's getting the memory's getting allocated on the heap, not on the stack that actually contains the product. Or it's only the pointer that ends up on the stack.
Mm-hmm.
That's two nights running. Well, two parts of the same video in which I've correctly identified and given information about C++.
It's growing on you.
Like moss.
Okay. So what happens here is the new operator will go... Well, actually, let's go ahead and walk through the entire execution of this first. Okay, when the program starts, main is invoked. So main goes on the stack. What's in main? A product pointer. What is a product pointer? Well, on a 32-bit operating system, it'll be 4 bytes wide. Then right here, we invoke the create function. So create goes on the stack. What's in create? Well, we can answer this without even looking at much of the code. We can answer this simply by looking at, does this function have any local variables? It does have a local variable. What's the type of that local variable? It's a product pointer. So what gets put onto the create stack frame when it gets pushed? A product pointer.
You could just draw a pointer symbol.
Product pointer gets placed on the stack. So I'm going to go ahead and delete these lines because I notice that I point to things quite frequently and then I don't erase the pointers. Not to be confused with this, never mind.
Arrows.
Okay, so this P is on the stack. This P is on the stack. However, when the new operator gets invoked, it allocates a product, not a product pointer, on the heap. Let's assume, just for sake of whatever, that a product is 128 bytes. So the main, when we're in the create, we're in the create function. So the create function is on the stack. This P variable, this local P pointer variable, is placed onto the stack and consumes 4 bytes of memory, again, when compiling on a 32-bit operating system and for a 32-bit architecture. However, when we invoke the new operator, a product, which for the sake of this example is 128 bytes, gets added to the heap. Where is the heap? Well, the heap's wherever the operating system decides to pull memory from. It's up to the operating system. That's not important. What's important is what gets returned by the new operator. The new operator, think of the new operator like a function. The new operator has a parameter list, which is a type, and it returns a value. The new operator will always return a pointer of whatever type we instantiated. So because we're instantiating a product, the new operator is going to return a pointer to a product. So the new operator is then going to fill this data on the create stack frame with a pointer to this data on the heap. So you'll notice, as of right now, the int main function, this local variable, is still pointing to unallocated or undefined space. Remember that variables don't get initialized in C++, meaning as of the create function being invoked, this variable is still undefined. However, the magic happens when we say return p. What happens when we return a p? This pointer, wow. This pointer gets assigned to the pointer that we assign the return value of create to. Which means that now that this stack frame is erased, and we're just working on main, now the main's pointer points to this thing on the heap. Do you always have to do type pointer name equals new type? Yes. I mean, yeah. That's if you were to instantiate a pointer, however, you would do pointer or pointer to type name equals new pointer thing. You get what I'm saying? The fact is, whatever's on the left side of the new operator has to have at least one more pointer symbol than whatever on the right side of the new operator. Because the new operator returns a pointer to whatever type you specified.
It's like the new operator gives it the place in memory, and the type gives it the amount of space.
Mm-hmm. The type will, yeah, the compiler knows at compile time how big product is.
Those being the two pieces of information it needs. It needs to know where to look in memory and how far to look.
Yep. And then it's just going to dump the pointer to whatever memory it allocated.
And it's just like, in fact, it probably is exactly the reason why, you can have a small C drive with programs installed on it that use, terabytes of memory if you've got them available on other drives. You can think of your C drive as the stack and your Z drive as the heap.
Yep. So if we make an unallocated pointer, the compiler still sticks 4 bytes of memory for that pointer. Yes. Remember, stack frames are initialized statically. I mean, well, not technically. You can get the illusion. I mean, technically speaking.
Let it suck it up. Speak simply.
Technically speaking, you can invoke a function an undefined amount of times, thus resulting in an undefined amount of stack frames being pushed. However, the compiler must know how big the stack frame for a function is, and that must be a constant value that doesn't change during the execution of your program. So as a result, a pointer will always consume however much memory it needs to hold a reference to somewhere in memory. Now, on a 32-bit operating system, because a 32-bit operating system can only address up to 4 bytes of numbers into memory, as a result, pointers on a 32-bit operating system and pointers on a program compiled for a 32-bit architecture running on a 30 or 64-bit operating system is always going to be 32 bytes. However, a program compiled for a 64-bit architecture running on a 64-bit machine and a 64-bit operating system will most likely consume 8 bytes. Yeah, stack equals static, heap equals dynamic. So this main function requires 4 bytes of static data. No matter what happens, no matter how much dynamic memory is allocated, the main function needs 4 bytes of static data. And that 4 bytes of static data is needed because of this pointer. However, the heap, we can still use the new operator to allocate additional memory on the heap and then have our pointers point to them.
So if, for example, your create method returned an actual product rather than a pointer for some reason, is that implicit in the that line in main, the conversion, or would it throw an error at compilation?
They'll throw a compilation error. If I were to erase this pointer symbol and have create return a function, or have create return a product, we'll get 2 compiler errors. We'll get one compiler.
Well, I meant if, yeah, obviously if you fix create so that it did correctly return.
Yeah. So if I had
a product.
So this is going to return a compiler, but if I fixed that, even if I fixed it, this would also return a compiler error.
Yeah. I didn't know if it, because there's aspects in that I've come across in languages where if you've got one of something and it's expecting some sort of wrapper around it, it automatically manages that. But anyway, it doesn't, so it doesn't matter.
Yep. So that should answer your question, the next question, which was, what would happen if you didn't have a pointer symbol after product create? You get 2 compiler errors. There's no implicit conversion between pointer and non-pointer types. In a second.
I'd come back to that one.
Yeah, I'll come back to the pointer and pointer one. But your next question, can you ever lose a pointer to the object on the heap? Yes, you can. And that's called a memory leak. So let's show you guys a memory leak.
With your steak.
Yeah. Let's show you guys a memory leak. This is code that is bad. Let's go ahead and show it.
This is where your computer blows up. Simple as that.
Okay, so how does everybody feel about line 26?
I didn't even get that far before I was disgusted. I got to line 24 and I went, oh no.
Oh, nobody's even answering. I thought it was the Friday class I was supposed to be asleep. Maybe it's just the time of day.
It's because, well, yeah, like I said to you, the people who are, well, this is from the early class, if you recall.
Right. Okay, so let's go ahead and fire up my task manager and watch my program crash.
And segful's turned up. How apt.
So you guys seeing this?
Not seeing anything you're typing. Just seeing your memory counter gradually increase. You might want to stop that before it gets...
I'm waiting for it to get to 2 gigs.
There you are.
Yep, there we go. This is as much memory as I can access on a 32-bit process. You'll notice what I get here. Unhandled exception, bad std bad alloc at memory location blah. I have just ran out of space that my... See, look at that.
Yeah, that's the memory equivalent of an index out of range exception.
Yeah. Pretty much. This is a memory leak. And memory leaks will destroy you and cause your programs to crash. And the only way to avoid a memory leak is to not write one in your code.
Don't do that.
It will happen.
And this is why actually it's a kind of almost a coding habit more than anything else. But you'll get into the habit of adding, well, it's like every begin has to have an end.
Right.
Every new has to have a delete. And you'll get in the habit of putting the closing. It's just like writing your parentheses and curly braces and stuff. You'll do them in pairs and then go back and fill in what goes in between. Mm-hmm. And that's a particularly good habit with something like this to get into. Because, and as somebody pointed out in BuzzNet, that was incredibly quick to go through 2 gigs of memory.
Well, yeah. Somebody did ask a good question, which was already answered, but I'll answer it again on video. They asked, do I have to restart my PC to reclaim that memory? And the answer is no. If you look at this graph in my performance monitor, you'll notice I allocated 2 gigs of memory, it stayed allocated while my program continued to run inside the debugger when it crashed and threw that exception. And then when the program terminated, it just plummets. This plummeting is the operating system reclaiming the memory allocated by my program.
Hurrah!
So now if I were to do this, and run my program, this will run forever. And I don't even know where it is. There it is. It's taking up one of my cores entirely of CPU, but you'll notice that its memory is stuck down there at 404K. And it's not going to grow.
Sorry, what was it you changed?
I did
I
a
didn't
delete.
see what. Oh, right, yeah, that makes sense.
So by adding this delete, we're still using 100% of our CPU, or like I said, one of my cores.
Well, yeah, we're still, as fast as possible, it is making
Yeah.
products and then getting rid of them again.
Yep, but the memory is staying constant.
And would that be 400 to run the console plus 4K for the product?
I mean, about. If I just run this, it'll...
Well, it was just the fact that it was 404 made me wonder whether it was 400 for that.
Well, 392, and then that's 8 plus 4, that's 12 bytes of additional memory that was allocated, which probably is in what string is. So if we see out size of product, I wouldn't be surprised if this turned out to be 12. No, 32. But anyway, that sort of closeness of monitoring memory isn't particularly useful because there's so much more going on behind the scenes that can impact.
No, I just wondered as a.
Oh, I wondered too. That's why I did that.
Yeah. So I tell you what. Why don't you go ahead and whiteboard out the answer to Raymond's other question?
Alrighty.
And then there may be more questions coming in by then, undoubtedly. So Raymond asked, can you show the pointers so we can visualize it?
Yeah.
Product pointer P equals new product.
I'm going to leave this up. I'm going to open up another document.
Parentheses pointer.
Ooh, you can tab it Windows. Well, that's pretty. Okay. So show a pointer so I can visualize product pointer P equals new product pointer. So product pointer P equals new product pointer. I'm not going to bother with the parentheses. I've forgotten the rules of parentheses if you don't have constructors. But this will compile. This code is valid. It will compile. Can anybody guess how much memory is going to be allocated on the heap? Let's assume that a product, don't answer this yet, a product is 128 bytes for this example. How much memory will this new operator allocate onto the heap? And I'm not picking segfault. Yep. This is going to allocate on the heap herb. Really?
Wow.
Herb? I don't know. The heap.
This is going to allocate on the derp. Yes. As Segfault says.
One product pointer.
That's what the shift key's for.
I need to learn how to do this myself without help. I will be able to draw one day.
But that's what the shift key's for.
Okay, so the stack will have a product pointer pointer. That is going to point to the product pointer on the heap. What does the product pointer on the heap point to? Nothing. However, let's say we do this. Let's get real crazy. Let's say dereference key equals new product. How many bytes is this new operator going to allocate on the heap? Yep. So again, let's assume we're on a 32-bit operating system. This is 4 bytes, this is 4 bytes, and then when this new operator gets invoked, we get a product on the heap. That's 128 bytes. Now to visualize this is going to be pointing to this. And there's an undefined amount of memory between each other. The amount of memory between each other is irrelevant. In this example, it's most likely going to be contiguous, but that's not necessarily, that's an implementation detail. That's an R, Gavin.
It's just what it looked like.
Okay, so we still, here's the cool thing. Even with this code, we still only have 4 bytes on our stack, because we really only still have a pointer pointer. The dereferencing of a pointer pointer isn't going to allocate any more memory on the stack, but the new operator will allocate additional memory on the heap. So now our chain looks like this. Our pointer pointer's on the stack, it's pointing to a pointer that's on the heap, and the pointer that's on the heap is pointing to a product that's on the heap. I'm saying that for the case of this example, a pointer equals 4 bytes. That's an implementation-specific detail. It's going to depend on the architecture you're compiling against, either 32-bit or 64-bit.
It's essentially, it's going to be a constant small number.
Yeah. It's going to be however much memory you can uniquely address.
So does that make that clear? I think that was as clear a description of that as I've...
Yeah, is everybody good with the pointer
yeah.
pointers?
It's just another form of hierarchical arrangement, as is most of programming, it seems to me. Just various forms of hierarchy, whether it's class to method to, you know,
yeah, it becomes a chain,
statement.
essentially.
Just in the same way that, you know, speech is the same. You've got letters to words to sentences to, or clauses to sentences to paragraphs to...
Yeah. But what's the point of pointer pointers? Point of pointer pointers is to assign a pointer to another pointer.
So that they can point to a pointer.
Yes. DirectX uses them quite frequently. Because DirectX will ask you to pass in a pointer pointer to something. And then what it does is it takes your pointer pointer, and because the actual pointer itself is on the heap, what it does is it can now modify your pointer pointer. And not even necessarily on the heap. Your pointer pointer could have easily been on the stack, as well as the pointer that your pointer pointer points to. Okay, just to have a little bit of fun.
Say pointer repeatedly.
Just have a little
However,
bit
if
of
you want to have slightly more fun,
I'm gonna do some just to see if people are paying attention. Have a little fun, draw something out. Or hold on, somebody did ask a question.
make them code something out.
Hold on, not clear on how dereference p equals new product causes product pointer to point to the new product. Why doesn't it make product pointer point to the new product? A product pointer can never point to a product directly. A product pointer may only point to a product pointer. Because the product pointer can never point to an actual product, it can only point to a product pointer, we have to instantiate and new up a product pointer onto the heap. Now we bring the product pointer onto the heap with the new operator, in which case we get a product pointer on the heap. However, if we want to tell the product pointer that's on the heap to point to something, we have to dereference the pointer, like we do right here. This is the dereferencing operator. So the type of this expression is a product pointer. This is a product pointer. It's a product pointer because we dereferenced the product pointer. And when you dereference a pointer, you get the type that it points to. And because a product pointer points to a product pointer, I almost got that without messing up. I was like
good.
on a roll.
I mean, the root of this is that, I mean, syntactically, pointer, I don't mean programming syntax, but the word pointer is you're pointing to something. That means you're making reference to something. When you dereference something, you're doing the opposite, which is why it unwinds like this. A product pointer
Dereferenced is a product pointer. You take off one of the pointers. Okay, I do want to point out something really fun, though.
Basically, count the asterisks and say pointer that many times, and you'll sound elite.
Yeah.
But it's kind of conceptually similar to having a list of lists. To me, at least. Nelson goes deaf when he's trying to draw.
Assuming this is an ampersand, can anybody tell me why this code could cause potential issues? This isn't necessarily a discussion about pointers, but it is something that people should be able to identify as an issue. No, we are assigning the pointer to point to something.
Because if you read that out loud, that says pointer p equals the address of p2, yes? Mm-hmm. No, it says address of p2. It's because you're the only person I ever hear say the word address out loud, and you say it wrong. And now I'm saying it wrong.
Okay. What happens with this code is now we have a real product. A fully fledged 128 byte wide product on the stack. And we are telling the pointer on the heap to point to something on the stack.
And no, NATO, not address.
So again, this wasn't like a huge, I'm introducing something new. This was I found a way to hopefully solidify people's understanding of the stack and the heap and point out that just because we're using pointers doesn't necessarily mean we're pointing to something on the heap. This code is bad because we are at the lowest level pointing to something on the stack, which if we were to ever return this variable from a function, that memory would no longer be available. Yeah, when the stack unwinds, the pointer won't be pointing at anything. Well, it'll still be pointing where it used to point. It's just where it used to point is
you have no control of what's going to be in there.
Yeah. So understanding these chains, understanding what exists on the stack and what exists on the heap is very, very important.
And that exists on the stack because of where it was called from, where it was created. Yes.
Yes, this code right here allocates one product variable onto the stack.
Actually, could you show that example in Visual Studio now? Just type that up
Yeah.
quickly. It might make it certainly make it easier to refer to line numbers and stuff.
So that example looks like this. Product, pointer, pointer, product equals new product pointer. So that's the first bit. And then product on stack, and then dereferencing our product pointer and assigning it to the address to product on stack. What this results in is a very potential and non-obvious bug.
Yeah, because I mean, if you're just scanning through that code, nothing about it leaps out at you particularly.
Right. If I was
it certainly wouldn't if it had, you know, some cover to hide in, like more code.
Segfault's leaving? Really? I thought this would be like your favorite lesson, Segfault.
We've been up all day.
Because it's pointers.
Ouch, kapow, wow, as Chris said. That's what she said, Chris. What did...
So here's what the function returned.
Nice. That looks like you're about to die in Minecraft. Not Minecraft, the proper version. Dwarf Fortress. That was just for NATO.
Okay, so yeah, this is a problem. If instead I were to assign the pointer to a instantiation of a product, and you'll see that we get a happy face.
Happy face.
Yes, there's a memory leak.
Nice catch, sir.
There's actually two memory leaks.
You passed Nelson's test.
There's actually two memory leaks. There's the memory leak caused by dynamically instantiating the product here, and there's a memory leak caused by dynamically instantiating the product pointer. Okay. Can I write the address out of each variable? Well, yeah, the pointer is at this. This is the pointer on the stack. This is the pointer on heap. Or sorry, that's the pointer on the heap. And this is the, hold on, I'm confusing myself. So that's the pointer on the heap.
That's right. Then dereference this line, I think.
And here's the pointer, the dereferencing of that will cause the pointer.
No, it'd just be a product.
Yeah, that would just be a product. That would be a product pointer. So there's the pointer on the stack. That's the memory address for that. That's on the stack because we are using the address of operator. Here's the pointer on the heap. This is the memory, the location that the new operator returned. And then that's the product on the heap. That's the pointer that was returned by this new operator.
And obviously that's the same because it's
it's
a pointer.
Different.
The point.
It's actually 4 bytes. It's actually
So it is. Sorry, I was.
40 bytes
I'm
ahead of it.
completely wrong on that then. Yeah. Sorry, I'm just being. Am I being? Yes. Sorry, I am being dim. I'll shut up.
Okay. Can you show us how it become a bug? This is how it becomes a bug. Well, not like this actually. This is how it becomes a bug. Actually, there's 2 bugs with this code as it stands. We all know that this is one of the bugs. Can anybody point me to the next bug? There is an actual other very important, terrible, horrible bug with our program as it stands. Besides the fact that, besides this is going to fail miserably, there's something else that's going to fail miserably.
Your face?
41. When we're deleting memory that was allocated on the stack, will cause you a very nice access violation, typically. Well, the reason this is a bug is because this product is allocated on the stack, and then I'm essentially returning a pointer to a product that's allocated on the stack. So when this function exits here after line 33, the stack frame gets popped, and the memory that was allocated for the stack frame is no longer valid, which means that pointing to it is no longer valid. It's just like this diagram. Where the stack has a pointer, which is pointing to a pointer on the heap. The heap has a pointer that's pointing back to an object on the stack. Once this stack frame gets removed, which is a thing that just happens and you have no control over, this memory is no longer going to be valid. Okay, now that I've successfully confused everybody, pointers you will rarely come across. However, the reason I'm actually, and a lot of books and stuff, they like avoid talking about pointers until like the last few chapters. But one of the things that got me actually thinking about pointers in a correct sense was the concept of a pointer. And that's why I'm introducing it here. And making it make sense is important. Well, in the code, notice that when the bad function is invoked, the stack frame required for bad function is pushed onto the stack. When this happens, the memory required for this product local variable is going to be allocated. Then I assign its name to this string literal, and then I set the pointer. This is what's going on here. This product on line 24 is the product that I'll just get my tablet out. This is line 24. This is the product on line 24. It's on the stack. However, what we've done is we've made this pointer on the heap point to this on the stack. Now, what happens when this function terminates? When this function terminates, all this memory goes away. And the product on line 24 becomes invalid. However, we're still pointing to it. When the function terminates after line 26, the memory I've made available to it on the stack is deallocated and made use of in different ways. Sweet.
Cool. So what's next?
What's next is Nelson needs a cigarette.
Okay, that's probably a good time to have a break then while you do that.
And after that, we're going to be building a dynamically sized array.
And then talking about homework, and then that'll be it.
We will go over what linked lists are, but we will not be typing out any of the code that has to do with linked lists because it is absolutely ridiculously fundamentally paramount to your knowledge and understanding of pointers and dynamic memory allocation to write a linked list implementation. I think that's like the #1 best example possible.
Cool.
No, not
all right,
type
well,
seg fault.
pause the video then, and you go off outside.
And we're back. So let's go ahead and let's create something fun. Let's do something fun with pointers. Let's use pointers and dynamic memory allocation, and let's make a dynamically resizable array. This is going to be very close to the algorithm used by the vector class within the standard C++ library. Let's talk about how we can do it.
Oh, okay. Thank you, NATO. And it's my fault, I was searching for the wrong name. No, well, yeah, they'll have to, you realise you're going to have to make them write a struct, not a class.
Yes.
Damn it, I should have answered. See, I was going to be all smug and say, oh, no, you're going to be writing a struct. But then this being C++, I thought I better not in case you weren't. Damn, I missed an opportunity to be smug. That's not like me. I know why I can be smug, because the Mariners got whipped today.
I don't follow sports.
No, I don't follow sports, but I've started following one again. And I was pleased to find that the first game I watched was the Mariners getting whopped. It made me think of you. I was just filling time while you tippity-tapped. Have you done?
Aww. This is going to be fun.
You done broked it. Don't you just love C#?
Oh,
Were you
wow,
hoping to debug your way through?
I'm stupid.
Oh, I thought you were intending to I thought you were deliberately, you were going to step through debugging or something?
No, I just made a mistake.
You were just being foolish.
I made another mistake. How embarrassing. Alright, so let's walk through this program really quickly. products equals new product 1, product count equals 1. We create a temporary products variable, then we reinitialize our our old products to product count plus 1, which will be, in this case, 2. We loop from 0 to 1. Oh, products I equals products I. Really? You let me do that?
I don't know any C++.
Oh, and I should probably use getLine instead of
Cin.
Wow. Where are we failing on again? Delete temp. Temp equals products. Ooh. I totally forgot about this. Okay. Quick thing for everybody who isn't aware. Actually, I'm going to go over this when I go over the rest of the program.
Generally the case, or is that just me being useless at...
No, that's off by one error is one of the most common programming mistakes. Okay, so now that I have finally fixed the program, you'll notice it does execute properly. So let's talk about what I did.
Which helps.
What I did was I made a dynamically sizable array. So, you are what?
Foncused. I think you meant focused.
Okay.
And Segful, if you get to the point where yours is the only name I can see, I'm going to slap you. Just
okay.
to warn you.
So let's run through this program. The first thing we do is we start with the struct product at the top and give it a string name. Simple stuff so far. Next thing we do on line 12 is something we haven't actually really talked about yet. I'm creating a product pointer, and I'm assigning it to null. What is null?
You're assigning null to it.
Yeah.
Not the other way around.
No?
You said I'm assigning it to null. You're not. You do this all the time when you say assigning. You get it absolutely backwards. 100% of the time you get it backwards. And because of what it is, I have to pick you up on it. You are assigning null to products.
Yeah.
Carry on.
Anyway, I am using the assignment operator with the right operand being null and the left operand being
Well, you see my point, though. It's because you're stating which you're assigning to what. And you did it earlier when you were talking about pointers. And it can be, because you're saying exactly the opposite of what is happening. I have to pick you up on that because you could be leading people astray. So, sorry.
Still.
But yeah,
so
carry on.
Null, what is null? Null is a special value in the C++ language that indicates a pointer is not pointing to anything. It's a special value in that it can be anything. I want...
Segfault said, no, it's just 0.
I want to point this out, Segfault, that treating null as 0, even though it is defined as 0, is not a good thing. The reason is null is a special value. Null is a special value that indicates that an array or a pointer is pointing to nothing. And it is subject to change within the specification to whatever it wants. In fact, there are some platforms where null isn't 0. Always use null to represent a pointer that isn't pointing to anything. Never treat it like 0. Just like how enums, we're defining a set of valid ranges. The set of valid ranges for a pointer are valid bits of memory that contain data that are typed to the type of the pointer, or null. Those are the only times that you should... those are the only things that you should ever assign a pointer to. So a null pointer is a pointer that's pointing to nothing. And unlike C# or other languages, null is all caps. Next thing we're doing is we're creating an unsigned integer product count and setting it to 0. And that's right to say, right? Setting it to 0? I mean,
yeah.
We're not setting 0 to it.
No, but we're assigning 0 to it.
Okay. So we're assigning a product 0 to a product count. Then we're entering an infinite loop. We're indicating the user that enter a product name or blank to exit. We are creating a temporary product object on our stack, and we are filling the name. Everybody good so far? We're entering a product name, we're creating a product on the stack, and we're setting its name to the input. If they entered blank, then we break. So straightforward UI. Then we do something interesting. There are two situations that might happen with the way I coded this. Products may be equal to null, or it might not be equal to null. In the case that products is equal to null, what we do is we instantiate a new product array with one product long. Then we assign the first and only element of that products array to the product that we previously created on the stack, and then we set our product count to 1. Now this...
That is essentially eating the error, isn't it? That's guaranteeing that if this was in a method that you knew were going to return something, you're guaranteeing that one exists rather than returning null as an option.
Yeah. Well, yeah,
Yeah.
But if they had just entered enter on the first line, then products would still be null.
But we wouldn't get that far. Because you'd break.
No, actually, that would work just... Yeah.
No. I mean, your keyword break. You're not. If they enter null, you're not going to get that far.
You wouldn't get that far.
So is that not never going to?
This is never going to execute incorrectly. This code is correct. However, at the end of the while loop,
no. What I mean isn't.
At the end of the while loop, products might still be null if they hadn't entered anything.
But if they haven't entered anything, you're not going to get to the end of the while loop.
No.
Because it's going to break. What I'm saying is lines 24 to 29 not unreachable, or lines 26, 7, and 8 unreachable because no, I'm being really quite dumb, I think.
I'm confused. You confused me.
Well, yeah, no, I'm. I can't see how you get past line 22 without products existing.
Because we don't assign products to anything. See, product gets assigned to name, gets assigned right here. Products. If you look, the first reference to products, if we start at the top, it starts on line 12. The only other reference to products is line 24.
Sorry, yes. Wow. Okay.
I can see it.
That's basic stuff as well. I think it was just the proximity of that. If it's blank,
oh right, yeah,
break, and then immediately saying if it's null. I was looking at it going, but it's already. Yeah, sorry. Wow. Okay, everyone, ignore the last 5 minutes of me, please. I don't want to confuse you.
Although Sagfeld asked, says I still have a memory leak. Where's my memory leak?
Maybe you don't.
Oh, he didn't see line 51 and 52. Okay, so we're saying if the array of products, or the pointer to products is null, then do this. Now we haven't seen this syntax yet. What this syntax is, new has two options. You can either invoke new without specifying a number, or you can invoke new with specifying a number. So we've seen doing this, which is valid, but now we are seeing doing this. This does something a little tad bit different. When you invoke new and you pass in an index like this, it instantiates a new array. The only thing you need to understand about this is that this is an array. It's a dynamically allocated array. And the corresponding delete call must be delete empty bracket temp.
If you missed out the empty brackets, will you get a helpful error, or will it just delete the first one?
I think I'll get a runtime exception if I'm not mistaken. Yep. Debug assertion failed. I get block type is not valid.
Oh, well, that's good. At least it doesn't let you do anything dumb.
Well, yeah, but it's not.
I mean,
It's,
well, it lets you do something dumb, but it tells you you've done something dumb.
yeah. What is product? Product is a struct that contains a single string. That's all it is. It's just a struct with a string name. It's the same product structure that we've been working on with most of our examples. Okay, so what happens here on line 26 is we instantiate a new array. And again, because we're using this syntax on the new operator, we must pair it with the corresponding appropriate delete statement. Then what we're doing is we're assigning the first and only element to the product structure that we previously have filled up from user input. This is a copy. This copies the memory from product that's on the stack into the memory that's on the heap, which is in products. Then we set product count to 1 because we're indicating that we have one element in our array. So that's the first iteration of the loop. So if I run through this, actually, stuff. This is the first iteration of the loop. When it loops all the way back around, products is now a valid pointer to an array that contains a single item stuff, and product count is properly set to 1. Now you'll notice that the next time we iterate over this loop, products will not be null. Therefore, this else statement will execute. What is this else statement doing? The first thing it's doing is it's aliasing out the old pointer into a temporary pointer. It's then instantiating a new array of the product count plus 1 and assigning it to our products variable. Then we're looping over everything that's in our old products array and copying it to our new products array. Then it's setting the product that we just added to the end of our new products array. We're incrementing our product count, and we delete the temporary variable.
All of which is very similar to what you were doing when you wrote out your bubble sort algorithms, except rather than swapping two things over via a copy, you're just copying it and adding one.
Yep, and then deleting the old one. If I had not deleted this temp, we still would have a temp array resident in memory that wouldn't get deallocated.
So each time through the loop, you would end up with more and more memory getting lost, actually, if you didn't have that delete there, because the array would keep getting longer every time it was reinstantiated.
Yep. So this copies the entire array and adds a new product. Yes, this is what this code does. It sets the old array to a temporary variable so we don't lose track of it. It instantiates a new array of one more element in width. It copies all the old elements from the old array into the new array. It adds a new element to the new array. It increments our product count, and then it deletes our old array.
All of which could just as easily be done with a list.add. Is it literally what list.add does?
Yes. It's a little bit more complicated than this.
Vector.pushback,
yeah,
as K73 said.
Vectors and lists work in this exact way, with the exception of every time it needs to increase the amount of memory it stores, it actually doubles it, so that it doesn't have to create a new array on every add.
It essentially takes the load off the CPU.
Yeah.
Fewer segfault.
So segfault asks, is product new product 1 the same as products equals new product? And the answer is no. The specifics behind this I am not entirely aware of. And I'm just going to have to say that because I don't know the exact difference between doing this and doing this, other than they are different. And this will cause me, hopefully, a nice little runtime exception. Yes. This causing me a nice little runtime exceptions. The reason why this is causing me a runtime exception is because the delete is using this syntax, whereas the new is not. So they're not paired up correctly.
Cool. So are there any more questions about what we've covered so far? Those of you with a print screen button would be advised to use it.
Actually, I do want to... I don't know if this will compile or not. Give me a sec. No. I forgot the... there's another bit of syntax that will hint the debugger to treat that value like an array, and I can't remember what it is. What is temp doing with products? Temp's not doing anything with products. Here's basically what's going on. Let me go ahead and bring up a whiteboard. Here's what's going on. We have a pointer, a product pointer.
Just draw the asterisk.
What am I doing? Called
C++ class.
products. And we're assigning it at this. Let's assume for now that this is the second iteration of the loop. So we're actually assigning this to a new product array of 5 elements. So let's just pretend this is what's going on right now. This is the fifth iteration of the loop. So what we need to do is we need to instantiate a new array, assign it to this pointer, and copy all the values that used to be in this pointer to that new pointer. So what we can do is we can say product pointer temp equals products. So at this point, the heap looks like this.
You've got to remember there is no way of changing the length of an array.
Right.
An array is a fixed size. So when you're adding something to an array, what it actually does is makes a new array that's a bit bigger and then just copies everything into the new array and nukes the old one. That's the only way you can do it.
Okay, does everybody understand this diagram so far?
It's Attack of the Killer Tentacled Heap.
At this point in the execution, both temp and products are both pointing to the same thing in memory. They're pointing to the first item in a product array. However, it gets a little bit more complicated because what we're doing now is we're saying products equals new product of 6 elements. At this point, products no longer points to this array anymore. Products now points to a newly allocated array on the heap. So now it points to P1, P2, P3, P4, P5, and P6. Products at this point in the program points to this. However, temp is still pointing to the old array, but products is now pointing to the new array. So now we're going to enter a loop. And I'm not going to write this out. But what this loop is going to do is it's going to take the data from each one of these old items and it's going to set it to each one of these new ones.
But wait, that leaves a space empty.
Yes.
That's disgraceful. You should shove something in it.
Yep. So, okay, remember this loop does this copy operation. However, at the end of this, there's still the P6. What are we going to do with the P6? We're going to say products at the 6th index, which is 5, equals new product. And I'm not going to use the word new product because that might get confusing with the new operator. So I'm just going to say product. What this will do is this will take the item in product and copy it into the final element of the array. Now what we can do is we can say delete bracket, bracket, temp. This line of code will jump all the way over here and delete this entire box. So now temp is no longer pointing to a valid place in memory. We've gotten rid of all the old memory. And yeah. So the first step is we instantiated our products array. And remember, for the sake of this example, this products array is the array that's already in existence. The next thing we do is we create a temporary product pointer and point it to where the product array used to be. Then we allocate an entirely new array with this. We instantiate a new product array with one element larger than the old array, and that gets allocated in the heap over here. Notice how we get 6 elements. Then we enter the loop, which the loop goes over and copies every item out of the old array into the new array. Then we set the last item on the new array to the new product, and then we delete the old array.
Cool.
So do we reassign product 6 to products? I'm not sure I follow.
I didn't even see that question.
It's in BuzzNet.
Then you shouldn't be looking at it. What's next?
Now it is. I still don't understand. Okay. So there's our code for now. This is the code that's doing exactly what I just described. Let's talk about splitting this up to multiple functions, because frankly, this sucks. This is highly unusable data structure. In fact, this isn't really even a data structure. This is just code. Let's turn it into a data structure really quickly. A really simple data structure. Let's call it inventory. Let's give inventory a product and a count. Now let's write some functions. Let's write init inventory. What's init inventory going to do? It's going to assign products to null, and it's going to assign count to 0. Then we'll have a function called add product that takes in an inventory and a product.
Pointer.
What is this going to do? This is going to do what this code does, essentially. So I'm just going to copy and paste it. And then change the variable names. This is going to say, if inventory products equals null, then do that, 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 that.
Yep.
Control backspace. Okay, so now we have our add product, and then let's have a method or a function called destroy inventory. This is going to be if inventory products does not equal null, then set inventory products to null. Or sorry, that was stupid of me. We need to delete inventory products and then set it to null. And then set our count to 0. Actually, I typically like inverting this code. How does everybody feel about my three methods, my three functions?
There's no way to take a product out.
And we're not worrying about that.
Cool. In that case, joyous.
Okay, let's look at how we can use our three functions now. Our three functions and our inventory structure. What I'm going to do here is I'm going to say inventory. I'm going to say init inventory at inventory. Or sorry, at the address of inventory. Then I'm going to say, at every iteration of the loop, I'm going to say add product at inventory, and then product. Then I'm going to loop over the inventory. So I'm going to say inventory.count, and then inventory.products at I. And at the end, I'm going to say destroy inventory. Okay, so let's just make sure this works first. Yep. Okay, we factored out all of this dynamic memory allocation stuff into three functions: init inventory, add product, and destroy inventory. Furthermore, we've abstracted out into a structure called inventory. So the structure called inventory is right here. Let's just focus on this for a second. The inventory structure contains a product pointer named products and an integer count. So it contains two fields. Does everybody understand the purpose of the inventory structure? It's there to contain an array of products and a size of how big the products array is. Okay, the first function we have is init inventory, or so
initialize.
Yeah, initialize init. I don't want to spell initialize. The inventory structure is a way for us to factor out additional code into different functions that we can reuse. So ignoring the other functions for now, looking about how is product pointer products making an array? Good question. It's not. It's just defining the existence of a product pointer. It's not actually making an array. That code that actually makes the array is elsewhere. And
remember, if there's no equals there. That's in exactly the same way that line 13 isn't. It's just defining the existence of an integer.
Right.
Don't let your pre-existing knowledge be confused or sort of blown out of the water by the fact that we're talking about pointers here.
Yep. And do not think about classes right now. We're not worrying about classes. I know that this is probably more confusing to the people who are going through the C# 102 class right now than it is for the people who aren't familiar with what a class is. But yes, we are in a way mimicking classes to an extent. And we'll be talking about how to make this code even better with the existence of classes later. Okay, so this is a structure that contains a product pointer and an init count. That's all it is. This is an 8-byte structure that just contains a pointer and an integer. No array is being created yet. However, the init inventory function takes the inventory, assigns the products to null, and then assigns the count to 0. So the init inventory function is important because it will initialize our inventory object to valid defaults.
Or constructed.
Yeah, or constructed. The add product function does the actual instantiation. When we add a product and our product's pointer is null, then we instantiate a new products array of one element. If our inventory products is not null, however, then we do what we described before, where we we assign a temporary variable, we instantiate a new array, we copy everything from the temp array to the new array, we add the element to the end, we increment our inventory count, and we delete the temporary. This is how our inventory structure turns into an array, or has an array in it, because of lines 26 and lines 33. These are where we're instantiating the array. We're deleting the array on line 42 if we need to. So if we add two products, we'll end up with a delete operation. The destroy inventory function says if the products array is null already, then just return. We don't need this anymore. This function is done. Inventory is null. It's not holding on into any dynamically allocated memory. However, on line 51 is executed if products is not null, in which case it deletes the products, it sets the pointer to null, and it sets the count to 0.
And strictly speaking, lines 48 and 49, they're an optimization. You don't literally have to do that, because that is the upshot of what happens in the next 3 lines. You're just saying, oh, we've already done that. I mean, this is the inner workings of a list. This is, as you have gathered.
This is how vectors and lists are implemented. In a rudimentary sense, of course. But this is how their algorithm works. Again, their algorithm is a lot more efficient in that it allocates more memory than it needs, which doesn't sound efficient if you just took what I said exactly, but it allocates a buffer so it doesn't have to continuously allocate more memory.
Well, it's that age-old thing of balancing CPU against memory.
I mean, if we had a terabyte of memory,
to use a little bit. Yeah, it's far better. Well, even not going that far, it's far better to use, another 128K of memory, or to go from 128K to 256K of memory, than it is to be accessing your CPU every cycle, creating a new thing.
And dynamic memory allocation is relatively expensive. Excuse me.
It's
Okay, how does the program know how much memory to release when you call delete on line 51? It just knows. The only way that I can think of this working, and again, here's the thing. The implementation of this is going to be standard library dependent. My theory, of course, and this is the theory that makes the most sense, is that when I instantiate a new array, some sort of count is actually placed onto the heap in addition to the product data. Now that's only going to be true for arrays instantiated on the heap, not arrays instantiated on the stack. And then when we delete, it knows how much memory is allocated. I do want to point out that, Gav, you're going to love this. Did you know that you can overload the new and delete operators? You can actually write a custom function to be invoked in place of these functions.
Why?
They're really fun, really fun. You can use them to write libraries that detect memory leaks. Because what you do is whenever your custom new function is invoked, it allocates more memory than it's supposed to, but it chains itself in a linked list. And at the end of your program, once everything is supposed to be deleted, you walk that linked list and find anything that hadn't been deallocated.
Okay.
It is fun stuff, but yeah.
It's 3 in the morning. I don't care.
Okay, somebody did.
Oh yeah, that does sound fun. Yes.
Well, I thought it was fun.
No, you can't gist that to them. It's what you're setting for homework.
No, it's not. We're doing linked lists. Totally different.
Well.
Okay. So because of this code, now I do want to point this out, everyone.
Can I just point out? I will say that don't. Because we've got into the habit of gisting this sort of things for people, and a fundamental rule of 3D Buzz has always been, and this does hold true, I'm afraid, when you look at things. Unless you code this stuff yourself, you're not going to learn it. Yeah, like you said, like Wolf said, you've got to copy it, not paste it, or not past it. But.
Well, no, the reason I send the gists is partially because people are complaining about the fact that they can't see everything on the screen, and it's really hard to balance that between a bunch of people who might be looking at different parts of the code.
I just wanted to make the point.
Yeah, well, it's
if
a
you
great
think
point to
you can
make. If you're not going to
go
copy,
through this and you're just going to copy the things out of the GIS, because fundamentally, I mean, you're doing quite a lot of the homework. I don't care what you it's going to involve changing some names and stuff. But, I mean, you're never going to get any better at it if you don't actually write it out yourself. And it does kind of beg the question, why are you even trying to get better at it? To what end? At some point, you're going to have to write your own code. Otherwise,
yeah, that's certainly
there's no point to this. If you don't enjoy writing code, what the hell are you doing here? Really? What
yeah.
I now know how to write code. I refuse to do so because I dislike it.
Well, no, but again, it's to combat the legitimate complaints people have been making about the fact that our examples are so large now that it's impossible to keep them on the screen at once. But if you don't write it yourself, then you are just cheating yourself. Okay. As a result of us doing this, you'll notice something interesting though. In an inventory, add product and destroy inventory all take in a pointer of inventory. That's very important. Although in our example, the inventory structure is being allocated on the stack, it's still important for us to pass it by reference, or sorry, not by reference, but by pointer, because passing by reference has a different meaning in C++. It's still important to pass it by pointer so that the other functions get access to the same object that we're working with. Does at least that bit make sense? How we have to pass in the inventory by address into all of the functions that modify our inventory. This inventory class, or this inventory structure, needs to be passed by pointer to all these functions, because these functions actually mutate the values of the inventory. If I did not have that as a pointer, what do you think would happen? Of course, all of the code will break until I switch the pointers to a dot. What happens now? And the answer is a copy of the inventory struct gets sent in. We edit a copy, and then the stack frame of this init inventory function disappears, and, well...
Nothing gets done to the original.
Yep. Yep, C++ does not have reference types. C++, whether or not a type is passed by value or by reference or by pointer is determined by the annotations that you give it in the signature, not by what kind of type it is.
Cool. Well, we're coming up on, well, we're over 2 hours into this 45-minute lesson.
Yeah.
Sub lesson.
Yeah, we're just about done. This is all the code I'm writing, but I am going to give a few more minutes for questions, and then I'm going to write out a linked list, and then we're going to be done. Not write out like type out, write out, show the diagram of what the data structure needs to look like in memory. And then based off what it looks like in memory, I want people to implement it in terms of that. But why did we add the address? The reason we added the address right here is because in C++, a non-pointer type is not implicitly convertible to a pointer type. As you see, the error says, no suitable conversion function from inventory to inventory pointer exists. So instead, we have to specifically turn our inventory object into an inventory pointer by using the address of operator. Okay. So, and now everybody sees this code. We now have a reusable product inventory data structure that we've coded from scratch and are not relying in any way off the vector class. And in fact, this is how the vector class works for the most part behind the scenes. Of course, it's a bit more complicated than that. It's a bit more efficient, but this is the basics of the vector implementation. Why would I do this instead of using a vector? I wouldn't.
For didactic purposes.
This is for data structures are the best way to learn pointers, period, hands down. This is for a learning purpose only. However, there will be situations where you decide you want a dynamically resizable array, in which case you now know how to do it.
But the thing is, Chris, at some point, somebody had to write the vector class.
True.
Struct, array, whatever the hell it is.
No, it's a class.
But you know what I mean? You know, somebody had to write this. At the end of the day, somebody had to write every single thing.
Yep. And for people in the C# 102 class, I do want to make one quick tiny little shout out that you'll notice some things that we're doing that look very similar, but we're doing it in a really lame way. This is how you did object-oriented programming in C. Next week, we will be talking about how to do object-oriented programming in C++ in a way that's a lot nicer than what you see right here. But this is the basic principle of object-oriented programming right now. We have our data held in a structure, and we have our functionality held in these functions that we invoke, passing a reference or a pointer to our structure as the first parameter. Just imagine this parameter right here was named this.
Gerald.
Instead of inventory. Anyway.
No, it's named Gerald.
No. Okay.
In the next class.
Yes, that's just in the next class. Be thinking about that. Okay. Any more questions about what I have here? So is everybody super excited to talk about linked lists? Please remind me what the pointer's doohickey symbol is for. Is that only for accessing things by a pointer? Yes. This syntax and this syntax, this is a shorthand for this. This dereferences our pointer and allows us to reach in and access the members of the object that is sitting behind the pointer.
Because remember, the product is a member of the inventory. It's not a member of the address of inventory. So you have to dereference first.
Okay, what I'm going to show you guys is the data structure for a linked list as it appears in memory.
So what exactly is a linked list that makes it special?
Well, a linked list is a special data structure that uses a collection of linked items together. So how is it laid out in memory? Well, we're going to be writing a singly linked list. So here's what the heap is going to look like.
I still don't understand how that differs from a list.
A list?
Or a vector.
You'll see. Let's say we have a struct called node. And the struct node has some members in it. These members you're going to have to come up with, but at the very least, has to have a very special member in it. A node pointer called next. How this looks like in memory, we could have node 1, bunch of other memory used for other purposes, node 2, a bunch of other memory used for other purposes, node 3, wow, 13. Where did that come
Watching
from?
too much House.
I haven't seen House in a few
back.
years. Really? I thought she died of her
Well,
brain
it
disease.
ends on Monday. No, the last ever episode is coming Monday. It was the penultimate. And there was a pointer to the next, which is next Monday.
Okay. What this heap diagram is representing are 4 instantiations of this node object. The n inside of each one of these boxes represents what this next pointer is pointing to. A linked list is where you have a data structure that is linked together by these next pointers. So this next pointer points to this node, which actually I probably should have just done this. This next pointer points to this node. This next pointer points to this node. This next pointer points to this node. This next pointer points to null. This is a linked list. Linked lists have different performance characteristics than vectors or C# lists. The biggest difference is that insertions into a linked list are constant. They always require the instantiation of a new node. However, deletions of a linked list are constant as well and very, very straightforward. The only thing you have to do to delete an item out of a linked list node is delete the memory and then set the previous node's pointer to null. Or sorry, set the previous node's pointer to the pointer after the thing. So deletions and insertions are both constant. Whereas in a...
So if you,
what?
So if you delete N3, what you have to do is go into N2,
Right.
set its arrow to point to N4, and then nuke N3. Otherwise, you've broken the links in the chain.
Yep.
But presumably, in order to get at N7348, you have to tell it to go and find N1 and then follow the list.
Yep.
Follow the yellow brick road.
That is the number one reason, that's the number one performance drawback of linked lists over vectors or lists. They cannot be indexed directly. That's why the linked list class in C# or the confusingly named list class in C++, which is a linked list, do not provide indexing operations.
Because it's just the wrong data type to choose if you want to do indexing operations.
Yep.
You shouldn't be using this data type.
What are the squiggly lines? The squiggly lines are other bits of memory.
Remember, each of those boxes, N1, N2, N3, blah, 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 is just a location in memory that goes on for however much space the node takes up.
So this is any other memory that was allocated. This is memory fragmentation. Yes, this is. Did I say doubly linked list earlier? Because I meant singly linked list.
No, you didn't.
Yeah, I said singly linked list. So there, Roy.
I think he was just referring to the fact that it looked like there were two links.
Oh, there's this STL has a
Anyhow.
linked list. Oh, sure. Okay. Do we do previous also? No. In this case, to keep things simple, just do a singly linked list. A doubly linked list is where each one of these nodes has a previous, and the previous points to, well, the previous node.
You should have so got them to do a directed acyclic graph.
That's a doubly linked list.
Who are you calling an oik? K73.
All right, again, these, I could just delete these if these are confusing, but I just wanted to, I wrote them specifically to illustrate that the memory is not necessarily contiguous.
Perhaps you draw other boxes.
Well, yeah, this could be anything else. See, this is a heap for a vector.
Does an actual linked list have a predecessor as well as successor pointers?
Does it what?
Does it have previous as well as next, an actual proper list?
Rolling Stone says that the C++ standard one does. I'm not sure about the C++, or the C# standard one I think does too.
Well, I just assumed the C# one would. Bad sectors detected on your hard disk. Your heap shrank.
Okay. NATO, this is the difference between a linked list and a vector. The linked, or the vector, stores each one of the items in a contiguous block of memory, one after another. So the only bit of information you need to understand about a vector in order to access all of the items is a pointer to the first item. At that point, you can calculate how to grab any of the other items by simply adding additional numbers to your pointer that starts off at the beginning. A linked list, however, is not contiguous memory. You must have a node structure that looks like this. And again, the squiggly line, I guess I'm not very good at squiggly lines. But the squiggly line means this isn't the only thing you want in your node. You want something else in your node. You want your value.
Which makes sense. Otherwise it would just be utterly
Pointless.
Yeah, I was trying to avoid pointless. But, it would be a list you can't store anything in otherwise.
Yeah.
Just be a way to waste memory.
So a node will contain the value and a next pointer. Remember what?
No, I was going to say, remember, a vector is what any sane person thinks of as a list. It's such a stupid name for it. Anyway.
Okay, so each node, when in memory, will require you to, in memory, to store the value and the next pointer. The next pointer is going to point to the next item. Your linked list, you should also have a linked list structure. This structure is not necessarily going to be on the heap, although it could be, but there's really no reason. This structure will have a single member, or it will have more than one member, but this is the most important one, called first. Yeah, no, we're wrapping up soon. There's no last, no need for last. But I can't leave until people understand what it is I'm looking for. So the homework is going to be, and originally I was going to say not implement it in terms of the last week's homework. Then I was going to say to implement it in terms of last week's homework. But how about this? Make your linked list class or structures and functions, and write a program that allows the user to enter as many items as they want, as many numbers as they want. What was that, Gav?
I just have a horrible feeling this is going to confuse an incredibly large percentage of the people taking this.
Just bear.
No. I mean, yeah. I just think I can see this causing people to cry. Essentially, Google linked list. What does Wikipedia have to say about it?
Use your linked list implementation to find the average of all numbers that the user entered and display it to the user.
So this is specifically going to be a linked list of numbers?
Yes. Now, if you want to have some fun, I would really encourage people who implement this and work on implementing this until you understand the linked list. And again, it might take some time to do that. But after you've done that, a fun thing that you can do that I would very much encourage doing, but I want to leave it as something that's ungraded and not technically part of the homework, but I really do want to suggest it, is replace the vector you used in last week's homework with your linked list class or structures. But, and this, So that's all I'm saying. This is ungraded bonus. I would highly, highly, highly recommend people doing for the experience of doing so. But this bit is going to be the actual homework bit. If that seems fair.
Can I leave you to...
what do you think, Gav?
Can I leave you to post the homework?
Yeah.
And you can word it exactly as, because I tend to paraphrase your things. And I think in this case it would be better if you gave a very specific instruction of it in such a way that it makes sense and readable.
Okay. What are linked lists good for? Linked lists are good for reordering elements is significantly more, or not reordering elements, but deleting elements is significantly easier in a linked list, as well as allocation times typically are better with linked lists than allocation times are with vectors or C# lists.
So, for instance, if you were building your own, let's say, audio stream buffer, all of this, in fact, if any of you have played around with buffering any way, shape, or form, this will all be cake to you, because it's exactly what you end up doing with that, is creating your own lists of things and how long they are and where they point to.
Can I use methods? Please use functions. That's using methods. That's going to lead up to next week's discussion. What can linked lists do that vectors can't? Nothing, really. Well, except for nothing really, except for the performance characteristics. Imagine how horrible the performance characteristics would be to delete the first item of a vector. You would have to completely instantiate a new vector, a completely new array, and do exactly what I demonstrated with adding a product. With a linked list, how do you delete an item? How do you delete the first item? Well, you just set your first node's pointer to the next node's pointer, and you delete the memory for the first node.
And yes, deadline, there will be an extra week to this deadline, so it will be, normally it's the following Wednesday, so it will be a week Wednesday for this. In fact, no, let's make it Friday of next week, so there'll be an extra few days.
NATO, will you be able to show up for the open office hours? I'm planning on scheduling that for...
If you say tomorrow, I'm going to slap you purple.
I'm debating...
We should do it next week, actually. We should do an open office hours next week after Friday's class for a change, because I often feel they get slightly shortchanged in that.
I still want to do an open office hours, maybe Thursday at 1 o'clock my time, which is 3 o'clock CDT, and from 3 o'clock CDT, I don't know what it is in GMT.
3 Central is 9 p.m.
So is that good for time? Because if I were to do it tomorrow, I'd have to do it at 5, because I have another private class tomorrow. I do really want to do it this week for people, especially the C# people and the C++ people, because we went through some pretty grueling concepts in both classes. You know what I mean?
Yeah. It just seems, because obviously we have, like I said, we have got essentially a reading week next week with no classes.
I said we don't have any classes next week?
No, Jason's off tomorrow morning, this morning for me now.
I thought I was going to do the classes next week solo.
Well, no, remember, when we actually put this timetable together, he specifically left a week out.
Huh.
So that we were only doing week 7 solo.
Okay.
Shut up. I think everyone needs a week to catch up. And they do from the amount of not handing in homework that I've seen from people.
Okay. Again, if you have any more questions, if the homework is clear, that's good. If you still are confused about how to do the homework, we can go over some more stuff on Thursday.
Yeah, no. Apparently, and as Dak Daniels just pointed out, there is a UDK class on Thursday. At that time.
That means I can only do it tomorrow at 5.
Which is, there's no, I mean, that's the middle of the night again.
I still want to do it.
Yeah, no, I'm just saying. This is...
It's not a class. I mean, I'd really appreciate it if you were there. But I would rather do it just with one of us than not do it at all. Just because the last...
I wasn't talking about me being there or not. I was talking about for the fact that this is still this is supposed to be part of the early class.
Right. It's just I have a class tomorrow, and I have a class, and we have C# on Thursday. Then I have a private class on Friday at 1 until, yeah.
At some point there will be an open office between now and the end of time. So keep your eyes peeled on the forum.
Yeah, you're welcome. I'll go ahead and schedule it for 5 o'clock tomorrow, and you guys are welcome to show up. But if you can't make it, or if that's too late for you guys, just wait till next week, because then we'll definitely have a time to put in an early open office hours for you guys. 5 p.m. PST, my time. PDT, sorry.
That's the same slot as today, 1 a.m. GM, 1 a.m. British Summer Time.
There's not Friday for me. I have a private class.
Let's we can discuss this further off video.
Yes.
We're just sort of wasting people on video's time now.
Okay. Sorry, people on
At some point there will be a live class.
Okay. All right. So how's everybody feeling? Because I'm about to go ahead and shut this down. I think everybody's dead.
Yep. Sorry, was I bitching? I was reading. I wasn't really paying attention, and my ears linked straight to my brain and said, "Yes, dead."
Okay. Well, I'm gonna go ahead and hit the stop button. And yeah, later.
Cool. Well done on picking up from the middle of things.